All right. Hi, this is Bobook Bike, continuing with these meteorology lectures. This is number 5. We're going to talk about precipitation. That's pretty fun, right? All right. Let's first talk about what a cloud is. We already have talked about that we need saturation for clouds, right? So relative humidity needs to be 100. There's another way we can get a cloud too, with condensation nuclei. We're going to talk more about that in a second. But for the most part, we can say that clouds have very light and small condensation nuclei. And you might just think, okay, why don't clouds fall? Um, well, they can be too light to pass the updrafts that are under them. So if we have a cloud, under the cloud, oh, we have updrafts like this, and these updrafts keep it up because it's very light and it can't go past that. Sometimes that can happen, and when it does, when it falls, we run into dry air. That causes evaporation, so it can't keep going. Um, so what are the ways that we form these cloud droplets? We call this nucleation. So the formation of cloud droplets is nucleation. There are two ways. This is the one that's common. And that's when we have condensation nuclei, and that's what I was just talking about. So when we have condensation nuclei, that is heterogeneous nucleation, and that's very common. This one is not common. Homogeneous, however you want to say it. That's not even spelled right. Sorry about that. Um, no, you don't need condensation nuclei this time, but it has to be below -40 degrees Fahrenheit. That's pretty cold. So, pretty rare. So you mostly want to know that heterogeneous is what happens. And we have the condensation nuclei are nice friends that help us to make clouds. Um, how can precipitation form? There are two primary ways that precipitation can form. Uh, collision coalescence and the Bergeron process. Collision coalescence is, at least in the United States, rare. We don't get this that much, okay? It's more common that we will see the Bergeron process. The collision, I almost combined those two words. The collision coalescence method is where we have warm rain, warm clouds, meaning we have no ice. Cold rain with ice is what we more commonly get, and that's the Bergeron process. But let's talk about both. So first, the collision coalescence. Um, so for the collision coalescence, we know that eventually water droplets might get to a certain size where they can fall, right? They get big enough. And the only way this can work is for them to be differing sizes. Here's why. Think about it. If you have some that are the same size, they're going to actually fall with the same terminal velocity. They're not going to collide. I mean, think about what that means. We're saying they're colliding, they're coalescing. What does that mean? Well, they're colliding, they're going together, they're coalescing, and they're getting bigger to rain that actually is something. Um, and so that's why they have to be different sizes, because if they are, then the bigger one will run into the smaller ones like that, and then they'll combine. So that's the key thing. They have to be different sizes or it doesn't work. But like I said, in the first place, that's not even as common. We mostly have the Bergeron process, and this is from cold clouds. And it must be freaking icy cold, but that's not that bad. I mean, not that bad. That's not that hard to do because we have the troposphere, and we know as the altitude increases, temperature decreases. So it's already going to be pretty cold up here to begin with. Here's a good cloud that's going to tell us something's going to happen right here. Got a cumulonimbus cloud right there. That's telling us, I see that right there. We're going to talk more about this soon. But that tells us, I think something's going to happen. I think we're going to get some weather right here that's of interest. Um, we have something called supercooled droplets, and it's what you would think. They are in freezing areas, but they're still a liquid. So you might think, how is that possible? Well, it only freezes if it hits the surface. Um, so when it's just in the cloud, it doesn't freeze. So that's how these are able to be liquid. Um, and here's something else that we gotta know. Okay. So remember what we learned about in the last video. We have relative humidity and we've got the actual water vapor present divided by the potential. So that potential, the possible um, water vapor, the SHH, it is way lower for ice because colder can't hold as much, right? Um, so that means it is actually easier for the ice to hit saturation. If this is smaller, then it's easier for us to hit relative humidity of 100, which means saturation. And water vapor is attracted to ice rather than supercooled droplets. So if we have, let's just say these are our supercooled droplets over here. This is our water vapor, and then this is ice. The water vapor is going to go to the ice. That's where we'll attract, and then the ice is going to grow. And these supercooled droplets are actually going to evaporate, so they turn into water vapor, and then they'll turn into ice. So that's the way that it goes. Everything goes towards the ice, and the ice gets bigger. Once the ice crystals are big enough, then they're able to fall. So think about what I just said. We've got we've got ice. The supercooled droplets are um, the water vapor, they're going to turn into water vapor and then they're going to turn into ice. And as that happens, it gets bigger and bigger. And when it's big enough, then it can fall. There are two primary ways that they can get bigger. The first is called accretion, and it's very simple. We just have water droplets, super cooled water droplets, and we combine that with ice and we get a bigger ice crystal. Aggregation is something already ice combining with ice. So that's we got accretion aggregation. It's pretty simple, right? All this stuff that we've just talked about, that happens all at once, and then we know eventually this is getting big enough, it's falling, and we have precipitation. And then the last thing that we're going to talk about is how do we know what kind of precipitation we're going to get? Um, well, obviously we know that's depending on temperature and not just temperature, but the um also even the distance um, between the bottom of the cloud and the surface and the temperatures at those points. So let's talk about rain first. Obviously, this is applicable to thunderstorms too, but if we have the collision coalescence model, we can only get rain. And that's because, like I said, there's no ice involved with that. So that's the only thing we can get there. But here's another thing that's important. It all starts as ice for all these. We start as ice, but for the collision coalescence, it is not, we only can get rain. And as you can see here, we started out as ice, but then we get to a certain point, and that's the point 32 degrees Fahrenheit, at which then it's too warm and it turns into rain. That happens all the time. So when you get a rainstorm in the summer, or even a thunderstorm, it starts out as ice. So that's important. Then snow, that's pretty basic. It's just look all the way through. We're not, we're staying frozen, okay? Temperatures below 32 all the way, cloud to the surface. Now, sleet and freezing rain, these are the two that people could get mixed up because they are similar. But as you can see, the difference is just between the graphs. And actually, this point here, as you can see, it's ice and then, oh, above freezing and then below freezing again. So what can happen is ice when it um, or water when it's falling, if it hits a surface that's frozen, it will freeze to it. That's freezing rain. Because see this distance right here, it's very small, so it doesn't have time to freeze again, even though that the temperatures are below freezing. Or sorry, even though it doesn't have time, it ends up just freezing to the surface because it doesn't have time right there. It's still rain. It can't go back to um, ice in time, so it just goes and it's like splat. It just splats on there and it freezes, and then we get this. The difference with sleet, there's a bigger gap here, and it goes back to ice, and so it just bounces off. And sleet is not really that bad at all. Like freezing rain is very dangerous. So that's why this is really important. But to recap, it's basically we get to a point where it's below freezing again. That distance is small for freezing rain, so it doesn't have time to freeze again, but it does freeze once it hits the surface because that's just what happens. Remember I said it, water that's or a surface that's below freezing will freeze water automatically. But it's different for sleet because it has time to go back into a solid. There's a bigger gap right there. And as a result, it just bounces off because it already is frozen. So it doesn't freeze upon hitting the surface. It already is frozen. So that's the difference. Um, remember what I said, the burr drawing process is a lot more common. That's it for this video. Thanks for watching.